SGLang reports 383.7 tokens per second from DSpark, a speculative decoder whose real trick is confidence, not brute force guessing. That result used DeepSeek V4 Pro across 8 NVIDIA B300 GPUs at batch size 1, which radically narrows the headline. So separate two stories: a reusable scheduling idea and one extreme benchmark that the sources never reproduce on desktop hardware. Speculative decoding spends extra compute drafting possible tokens, hoping the target model can approve several while taking fewer decoding steps. But at batch size B with k speculative tokens, the target verifies B times k tokens, so heavy load can erase savings. DSpark targets both sides with a block drafter that preserves acceptance and verification windows that shrink when guesses look weak. Its semi-autoregressive drafter emits an entire gamma token block in one forward, while a lightweight head preserves sequential conditioning across positions. A lightweight sequential head using Markov or recurrent conditioning lets each position depend on the previous drafted token. A confidence head scores each drafted token's chance of surviving verification, turning a token block into a measurable risk profile. DSpark multiplies those token scores across the block, producing a survival probability for how far the entire drafted sequence may hold. Raw confidence is calibrated with sequential temperature scaling, so predicted survival better reflects the acceptance rate used for scheduling. Each step, the confidence scheduler converts block survival into a verification budget for every request, rather than imposing one fixed width. Static mode verifies the full drafted block every step, making it the simple baseline against DSpark's production trimming path. Compact mode verifies only the window selected for each request, making variable length trimming the intended production behavior. Cap accept verifies the full block, but commits only through the chosen window, revealing what compact mode would otherwise leave unobserved. Together, static supplies the baseline, compact supplies real trimming, and cap accept measures the acceptance ceiling that trimming hides. One request may verify 2 tokens while another verifies 6, so a fixed shape CUDA graph cannot represent the batch cleanly. Padding every request to full block width would technically fit, but it computes the very tail DSpark tried to remove. SGLang front packs each request scheduled tokens into one compact buffer, preserving ragged lengths without computing a full padded rectangle. The packed total rounds upward, only to the nearest captured CUDA graph tier, not to every request's maximum possible width. When budgets shrink, the packed total reaches a smaller graph tier, reducing attention and MLP rows instead of masking full-width work. Under data parallel attention, ranks share the largest required tier among them, then step down together when the packed workload permits. The packed buffer uses variable length metadata, letting compact verification reuse supported attention kernels, including DeepSeek V4's sparse MLA path. Compact mode stops after its chosen window, so the system never directly sees how many later draft positions full verification would accept. Cap accept restores that view by verifying the tail while committing the same output compact mode would have committed. For production runs, a block accept estimator uses future target token log probabilities to estimate the censored tail and its uncertainty interval. That estimate assumes anchor token behavior remains similar between trimmed and untrimmed trajectories, so it is observability machinery, not ground truth. SGLang calls its confidence scheduler a preliminary vanilla version and compares dynamic compact budgets against full block no trim scheduling. At batch size 1, target verification barely slows with extra tokens in this comparison, so dynamic trimming and no trim effectively tie. As concurrency rises and throughput plateaus, shorter verification steps matter more, allowing compact scheduling to pull ahead of full block verification. The lower acceptance example benefits earlier and more strongly because weak predictions leave a larger speculative tail available for trimming. Those two workload examples also differed in prompt formatting and round count, so the authors interpret the trend, not cross-panel absolute numbers. The current speed model and calibration fit are first approximations, and context length effects may shift the scheduler's exact operating point. Homogeneous batches hide the central benefit. Predictable and difficult requests sharing one batch should not receive identical verification windows. DSpark sizes each request independently, using confidence to grant longer windows where acceptance looks likely and shorter windows where it does not. In one mixed test, average windows measured 5.24 tokens for GSM-8K, 3.78 for Arena Hard, and 2.91 for Poetry. Despite those different budgets, utilization against the untrimmed acceptance ceiling remained between 0.88 and 0.97 in that example. About 55% of GSM-8K steps filled all 6 positions, while roughly 80% of Poetry steps used 3 or fewer. SGLang supports DSpark on dense and sparse models, naming Qwen 3 and DeepSeek V4 as examples of the 2 draft side paths. On DeepSeek V4 Flash, with 4 H200 ranks, DSpark led the shown throughput latency sweep against MTP and non-speculative decoding. Within that figure, all 3 arms used identical conditions except their speculation configuration, making the comparison internally controlled. SGLang says hardware, engine, and traffic differed from the DSpark paper, so it reproduced the mechanism and curve, not digit-perfect results. To convert smart scheduling into wall clock speed, SGLang cuts each step's cost and hides scheduler work behind the model forward. Small operations for compact scatter, page indexing, verify length scheduling, and ragged packing were rewritten as fused Triton kernels. The block drafter's sampling path also folds into fused kernels, while its matrix multiplication is sharded across the available parallel work. In one profile, work outside target verification shrank by 1.7 milliseconds, measured against a 7.3 millisecond verification stage. SGLang's existing overlap scheduler runs the next step scheduling alongside the current forward, leaving almost no DSpark-specific plumbing. Forward results return as asynchronous futures, while device-side barriers and on-device page tables remove per-step host synchronization from this path. DSpark relays confidence through the same asynchronous channel, reading the signal 2 steps later to keep scheduling off the critical path. With overlap enabled, the shown batch 1 decode loop loses its per-step bubbles and becomes about 1.5 times tighter. The scheduler estimates step time as a fixed bias, a batch size floor, and a verification token cost tied to total processed tokens. The batch size floor includes draft work and part of attention, so trimming can recover only the target's marginal verification token cost. The scheduler's optimization balances expected accepted tokens against measured marginal cost, so longer windows win only when their likely value justifies computation. The reported 383.7 figure combines these optimizations on DeepSeek V4 Pro, TP8 B300, batch 1, at acceptance length around 5. SGLang V0.5.16 ships DSpark, enabled with the DSpark speculative algorithm and compact ragged verification for the highlighted production path. LMSYS published the technical announcement on July 6, 2026. And the SGLang V0.5.16 release followed on July 2005. Neither verified source reports 383.7 tokens per second on a desktop GPU, so transferring that number to ordinary local hardware is unsupported. For local AI builders, the supported lesson is architectural. Confidence can reduce wasted verification, but achievable speed remains hardware and workload specific. Next steps include stronger adaptive cost models, better scheduling, broader model and parallelism coverage, production observability, and tougher CUDA graph testing. Remember both facts, 383.7 tokens per second and 8 B300 GPUs. DSpark's scheduling idea is the breakthrough worth carrying forward.